Okay, let's talk about the noise. Okay. Yeah, noise is very important in analog circuits. Noise. Because noise determines minimum input signal level that can be amplified. Yeah, there is equivalent input noise voltage. Yeah, for some amplifier, we have an amplifier, and then we have equivalent input noise voltage, something like that. Okay, all the noise inside this amplifier is reflected at the input. Okay, then we cannot amplify input signal smaller than this equivalent input noise voltage. That's the minimum input voltage level that can be amplified. Okay? Yeah, in a transistor MOSFET, we have flicker noise and the thermal noise, right? Thermal noise and then flicker noise. Yeah, this flicker noise is, there is a source drain, and then electrons are flowing along surface, right? But this, at the oxide and the silicon boundary, there is some trap. Actually, that trap determines this flicker noise. So there is a trap with a very large time constant, many traps in the large time constant, then small time constant. It captures that electron passing by and then release it after some time constant. Okay, so in a frequency domain, that noise is something like that. Noise power is this is a noise power spectral density. It's proportional to 1 over f. There are many traps with a small time constant. There are small traps with large time constant. Small traps, small number of traps with a small time constant. And then thermal noise is just a random Browning motion. Electrons passing by, it just move around. Electrons, this is my free electron. There are silicon atoms here and there, and then it goes a random motion, right? Browning motion. Even though there is electric field, net movement follows the electric field, but it undergoes a very irregular thermal motion. Because of that, we have a thermal noise. Okay, so this power spectral density of flicker noise is just something like KF model parameter, drain current AF model parameter, WLCOX times frequency, EF. EF is close to 1. Right? This is power spectral density of drain current between drain and source. And then we have another thermal noise, power spectral density of drain current due to thermal noise is just 4 kTr or something like that, or R squared. That's current, right? Yeah, this is simple model is we have 4 times 2/3 kT times GMB. GDS, something like that. So we have two kinds of noise component. So we can represent this one into something like something like that. Okay, actually, yeah, something. We can put it like here. There. So this drain noise is moved to the gate side, right? Then this voltage, this VGN F square is just GM square because it's reflecting the gate. Eh? Yeah, sum of those two divided by GM square. That's my gate noise voltage. Okay? So I move noise between at the drain and the source into gate, right? If I keep on continuing that, I can move all the noise voltage into input node of amplifier. That's equivalent to input noise voltage. Okay, question? Nope. Okay, let's go to SPICE for that. Let's see, where is my noise simulation? Noise. Oh yeah, here. Edit. So here I have a level 55, which is a V symbol. Mine is here 1 micron. Oh, actually, I have a. Let's try this one first. The first one is. Can I put? Oh no, I cannot do it. One by one. The first one is W equal 10 micron, L equal 0.7 micron. Then, at the gate source voltage, I apply this gate node AC1. I don't know whether you can see it or not. And then DC gate voltage 0.5 volt. AC small signal voltage AC1 is in series with DC 0.5 volt. And then I used some current controlled voltage source here. This VDS is, what's a VDS? VDS is just a current, drain current, okay? This VDS, IVDS is just a drain current, and then gain equal 1. So current, drain current is multiplied by 1. That becomes a voltage drop between HD node and 0, okay? So I use the DAN noise, which is output input. My output is just voltage source HD. This DAN noise requires voltage instead of current. So that's why I use the current control voltage source to put voltage here, okay? Output voltage. That's just, drain current, right? This is input. So it shows you some noise transfer function between input is a gate source node and output is just this one, drain current. And then there is this decade 10 means when frequency changes by 10 times, I put 10 points in between logarithmically, starting from 1 kilohertz to 100 gigahertz. Okay? Then let's simulate it. So do I have a noise analysis here? Oh yeah, here. So I have a output noise spectrum. This is actually current. Input noise spectrum. This is a gate node voltage. Okay. So horizontal axis is frequency, and this y-axis is power spectral density. Okay. This is a power spectral density of drain current. Drain current noise. See, you can see this is summer noise here, and then some corner frequencies around. This is flicker noise, right? Corner frequency is around 100 kilohertz, right? 100 kilohertz. And then this is actually what? Gate noise voltage. Power spectral voltage density of gate noise voltage. My GM is so small, so this VM becomes pretty large, 10 to the minus 14. So this is some low pass filter effect. Neglect this part. Just flicker noise and summer noise, okay? So this is for the, for the W equal 10 micron. If I change W equal 1 micron, what happens? Let's see. For the small transistor, okay, for the small transistor, I simulate a graph. What's my noise? Okay, where is my noise? Oh, here. So here my noise is output noise, input noise. Okay, log. So if I compare this one into this, so the left one is for 1 micron, right? W equal 1 micron. This right one is W equal 10 micron. Oops. Yeah, for the noise spectrum of current, drain current, let's see which is larger. Let's look at the thermal noise, 10 to the minus 25. Yeah, this is larger, right? Is this right? 10 to the minus 25, 10 to the minus 26, okay. Drain noise is larger in W equal 10 micron. How about the gate noise voltage? Gate noise voltage is larger for the W equal 1 micron, okay? So my gate noise voltage becomes larger for smaller device because GM is small in W equal 1 micron, okay? For small transistor, I have a large gate noise voltage. Okay. But to reduce input noise voltage, I need a large device, large W over L, and also large W n times L, okay? Yeah, for small VGN, I need a large W over L, and I need a large WNL, okay? This is for low thermal noise. This is for low flicker noise, okay? So anyway, you need a large W and a large L to reduce noise, okay? Yeah, question? No? Okay, let's continue with the gate capacitance model. Yeah, this is my gate, and this is my source, my drain. Yeah, this is a P-type substrate, and then this is a depletion region. Yeah, when surface is inverted, I have free electrons on the surface, right? Then I have some gate charge. Say there is some gate charge, plus. on the bottom of a gate electrode. So there is some electric field. Yeah, this gate charge generates a capacitance, right? CGG, CGD, CGS, CGB, something like that. Okay. Yeah, this CGG is just change of gate charge with respect to change of gate voltage. You know? CGD is change of gate charge with respect to drain voltage. Okay? Something like that. So when VDS equals 0, yeah, this is 0 volt because this is a source. And when VDS is 0, you know, there is a symmetry, right? So this gate source voltage will be half WL and this gate drain voltage will be half WL right? Yeah, in saturation region, yeah, this becomes very large, like a VDD. Then it becomes, it enters the saturation region, right? Saturation. Yeah, when saturation region, my inverter charge here, this is pinched up. So this charge, amount of this charge is around 2/3 WLCOX VGS minus VTH. This is amount of inversion channel charge. Okay, my QG will be sum of this inversion channel charge plus this depletion charge. Depletion charge is here, Q depletion. So this QN has no drain source term, right? So in a saturation region, yeah, in a saturation region, my QG becomes plus some depletion region, which is WLCOX gamma square root 2 pi f minus VBS or something like that. So this part is depletion charge. This part is inversion charge. Okay. So here, see, your CGS is 2/3 WLCOX, right? CGD equals 0. Yeah, CGB will be something like that here. Actually, there is some overlap capacitance component. Okay. Yeah, that overlap component generated because of this gate overlaps with the source drain, right? So this part generates CGDO. This part will generate CGSO. Okay. Yeah. Question. Okay, let's look at the sparse simulation of a capacitance model. So we'll try to generate the capacitance plot by increasing gate voltage, something like that. Say if I increase the gate voltage like that, you know, I just increase it in a linear way. So yeah, then I can monitor some drain current. The current is just CGG, something like that. My drain current is say I think my VDS equals 0. Then my ID equals 0. DC current is 0. This is CGD times that one. Yeah. my bulk current is CGB times something like that. So if I monitor some current, then I can plot capacitance. Yeah, let's look at my capacitance value. Oh yeah, here. Okay. Yeah, 10 by 0.7 micron. So my gate voltage sweeps minus 3 piecewise linear. This means time 0 minus 3 volt, time 6 microns 3 volt, right? Okay, then see I monitor the monitoring voltage source. So I put some transient analysis, print out some current of voltage source, right? Okay. Simulate graph. So this is a CGG, this is a CGD, CGB here. Okay. So this is a gate source voltage, drain source voltage is 0. So this is minus 6 volt, minus 3 volt to plus 3 volt. I remember this is a CGG, CGD, CGS are the same. This is a CGB, gate bulk. So let's look at the total capacitance. This total capacitance value is what? Oh, I cannot find the value. Okay, here. It's around, wow, how come this is pretty large? Oh, I have to calculate 10 to the minus 6 because of sweep rate. So it's around 30 femtofarad, okay? 30 femtofarad, the total gate capacitance for 10 by 0.7, okay? This Y value is multiplied by 10 to the minus 8. Question? Okay, let's stop, pause.